So today I will present the result that I published with a collaboration with Krzysztof Turzyński last year. So it was before I joined Nicolaus Copernicus Astronomical Center. I hope you will enjoy. So today's talk will be about inflation and specifically about geometrical destabilization. This is the phenomena that is known for just a few years, I think. So let me start maybe not very standard way. Let me just argue why we should care about inflation at all. So I will go backward in time. So first of all, quite current in the sense of the cosmology observations. As you see, redshift around 0 point something shows that our universe is quite homogeneous. So the largest structures that we observe in the universe are at the sizes of the small, which are smaller than 100 megaparsecs. So at the scales larger than this, the universe seems to be homogeneous. Moreover, we are quite sure that it was isotropic during recombination because we observed the cosmic microwave background radiation with its very tiny fluctuations. And the very first period of the evolution of the universe that we know with quite high accuracy is Big Bang nuclear synthesis. And it is quite fragile thing, and it's quite sensitive to how the universe behaved during this period. And it turns out that it was dominated by the radiation. So let me sum up. So first of all, it seems that our current universe is homogeneous at this case larger than 100 megaparsecs. Moreover, we are pretty sure that it was isotropic during recombination with the relative fluctuations of the CMB radiation temperature of the order 10 to minus 5. Finally, we know that it was dominated by the radiation during BBN. And in fact, the BBN is the very earliest point in time that we are sure about. So more or less everything that happened earlier, and we know that a lot of things had to happen earlier, are rather hypothetical than we have some strong knowledge about this. And this observation that I mentioned briefly is the base for so-called lambda CDM model. And this model is quite successful, fits quite well the data, however, has its own peculiarities and its own problems. And let me just mention a few. So the first one, the horizon problem. So if you extrapolate in the past from the BBN to the Big Bang, the evolution of the universe as it would be in the radiation domination era, it turns out that the observed today CMB comes from the patches of the universe that was not in the causal connection at all from the Big Bang. However, the temperature of this observed CMB is more or less the same. So there is a puzzle here. Why the causally disconnected patches produces the CMB, which is of the same temperature. Moreover, it seems that our universe is quite flat. And the flatness is not a thing that we would expect from decelerating universe. In fact, if there's some deviation from the flatness, the decelerating universe will accelerate these deviations. I don't see the chat, sorry. Is there any question about what I'm talking about?
I can't see anything in chat.
Okay, so that's strange because I heard some sounds like a chat. Okay, so let me proceed. Sorry for this. So I was talking about the flatness. So our new universe seems to be flat. However, if there was some deviation from the flatness, the decelerating universe, as evolving through the radiation domination era or the matter domination era, would increase this deviation. So the deviation from the flatness increases when the universe is decelerating. Finally, the most hypothetical one, but historically very important, the magnetic monopoles problem. So in fact, the question is why we don't see all the leftovers after the early evolution of the universe. Some heavy particles, some heavy stuff that probably could be produced in the very young, hot and dense universe. So initially, it is called after magnetic monopoles. So initially, the magnetic monopoles was this leftover about which the people are thinking, because the giant unification theories are on top there, and they predict that magnetic monopoles should be produced in the early universe. And the lambda CDM plus GAT predicts that there should be a lot of it, this magnetic monopoles, and we don't see them. So what happened to them? And it turns out that the inflation solves all these problems. And the inflationary hypothesis just assumes that the universe went through the period of the accelerated expansion in its very early times. Moreover, such a period produces very natural explanation from the inhomogeneities of the CMB that are observed today. And in fact, this inhomogeneities was recently a very hot topic, because from the Planck satellite, we got very precise data. And for the first time in the history of the inflationary models, we were able to rule out some of them. So a very large fraction of the inflationary models, one that was very promising, was ruled out by this data. And here we see a very famous plot from the Planck collaboration, which shows the bounds on the primordial field. So how the spectrum of the fluctuation deviate from the scale-independent one, and so-called tensor to scale ratio, so how much gravitational waves was produced during inflation. And as we see, there are a bunch of the models that fits quite well the data, and I would like to stress that the quite significant part of what alpha attractors predicts fits quite well what is obtained from the Planck. So the alpha attractors are denoted by this yellow region. And these alpha attractors are very promising models. They got quite natural explanation for the flatness of the potential that is necessary for the inflation. So first of all these alpha attractors comes from supergravity, and the simplest model is so-called T model, which is characterized by the potential in the following form and the scalar potential in this form. So this S superfield can be easily stabilized during inflation, and what we really care during inflation is T superfield, which has two real scalar components, which I will denote phi and xi. And if we do all the superspace algebra and so on, and remove everything that is not necessary for the inflation, just let these two fields talk, we'll get the Lagrangian density in this form with the potential of this form. And what is important is the kinetic terms of the fields. So the spectator, as I will call psi, has canonical kinetic term. However, the inflaton phi has something extra. There's a factor that makes this kinetic term of the inflaton non-canonical. And first of all, this is a key to producing the flat effective inflationary potential. And at the same time, it is the key feature that produces the geometrical destabilization in this model. So, in fact, we can think of these non-canonical kinetic terms as the kinetic terms for the field that has that are living on a non-trivial field space with some non-trivial geometry. We can associate the metric with this field space in this form. And it turns out that the curvature of this field space is negative. And this opens the window for the geometrical destabilization. So in fact, there are two scenarios. One scenario is such that the geometrical destabilization takes place during inflation. And this is in fact a problem for theoretical physicists, because this can spoil the inflationary model, because this will produce the deviation in inflationary trajectory, or can even lead to premature end of inflation. And the other case is that the geometrical destabilization takes place after inflation. And this is quite helpful for theoreticians because it helps to reheat the universe. So before I will go to the details of our results, let me generalize what we observe for this T model. So we can think about the T model as a sum model in the family of nonlinear sigma models. So we can imagine a quite general class of nonlinear sigma models with the action of this form, where there are a bunch of scalar fields that got canonical non-canonical kinetic terms and some potentials. So these non-canonical kinetic terms can come from the UV completion of the theory, so as in alpha attractors from supergravity, or you can imagine that you need to include them because they can be produced from some heavy particles, and if you want to produce some low energy effective theory, then you need to include some higher order operators, and these operators will modify the kinetic terms of the fields, making them non-canonical. So let me somehow summarize. So if you have some non-canonical kinetic terms, then you can interpret this as a manifestation of non-trivial geometry of the field space. So you can use like Riemann geometry to study this. You can introduce the metric, the Riemann tensor, the Ricci tensor, the Ricci scalar, and so on. And if this Riemann tensor that you associate with this metric of the field space is non-trivial, then the field space is curved. And in such a curved field spaces, quite important things can happen. So talking about inflationary models, if you have some generic nonlinear sigma model, then in order to obtain an inflationary trajectory, you need to solve the following set of equations. So the first two are just the familiar Friedmann equations. And the last one is just a set of equations of motion for the scalar fields in this model. And in fact, the only modification is that you need to take care about the movement in the field space. So you need to use the covariant derivative in the field space. Obviously, here we are using a spacetime that is spatially flat, and it is just Friedmann-Robertson-Walker. So the covariant derivative in spacetime is quite simple, and this is usually treated as just some Hubble parameter and so on. So this is the quite standard thing. In the case of the model, in fact, you can just care about the inflaton, so the phi field. And if you are if you are interested in the inflationary trajectory, of course, because everything else about so the geometrical destabilization requires two fields at least. So talking about the inflationary trajectory in T-model, you can neglect the Xi field because the very nice feature of this model is such that the Xi equal to 0 is the attractor of the evolution of the system. So the inflationary trajectory will be exponentially close to Xi equal to 0. So if you set the Xi to 0, then the potential of the model is of this form. And now we can easily imagine how it looks like, because everybody knows how the hyperbolic tangent looks like. And even it's easier to imagine how the square of the hyperbolic tangent looks like. So there is an inflationary plateau for large values of phi, and close to phi equal to 0, there is a minimum of the potential. So the inflationary trajectory is just the solution of the equation of motion for the inflaton coupled to the Friedman equation. In generic model, we can consider, so around this inflationary trajectory, we can consider the linear perturbations. And in generic model, the second order action for this linear perturbation is of this form, where we use the well-known so-called Mukhanov-Sasaki variables. And the important here is the mass matrix, which takes this form. Obviously, the equation of motion takes this form. And I want to discuss for a while this mass matrix. So the first term is quite familiar. So it's generalization of the Hessian of the matrix. So something that you would expect for the canonically normalized. So the fields with the canonical kinetic terms, there should be just the Hessian of the potential. However, in case of non-canonical kinetic terms, there are two extra terms. So the second one, which is just proportional to the deviation from of the inflationary trajectory from the geodesic in the field space. And the last one, which is the most important for us, takes its origin directly in the geometry of the field space. There's obviously the Riemann tensor here, which encodes the geometry of the field space. So in the case of the T model, we can produce the explicit expressions. So the evolution of the Mukhanov-Sasaki variables is determined by these very simple equations. And for the inflaton, the effective mass is just a Hessian of the potential. So something very standard. However, for the spectator, there is an extra term, which is proportional to the Ricci scalar. And for the T model, this Ricci scalar is negative. So if the velocity of the inflaton is large enough, this second geometrical term can dominate the sum. It contributes with the negative value, so can drive this whole effective mass of the fluctuations of the spectator to tachyonic values of the negative one. And this indicates the possibility of the geometrical destabilization. So the geometrical destabilization takes place when the effective mass of the spectator tends to be negative, so the fluctuations are produced. So in order to get better understanding of this linear perturbation, at least during reheating, where the inflaton leaves the inflationary plateau and oscillates non-harmonically around the minimum, we can first of all rewrite the equations of motion for the fluctuations using the Fourier transform to get rid of the to exchange the spatial derivatives with the multiplication by just wave vectors. And then we can rewrite this as a first order ordinary differential equations, as we see here. So the important thing is that finally we have the first order derivative of a vector multiplied by the matrix, which is, or just matrices, because there is one for the inflaton and one for the spectator. So this matrices are nearly periodic. So in such a case, we can approximate this using the solution using the so-called Floquet theorem. So the Floquet theorem states that in the system like this, so where the matrix is in fact exactly periodic, but we can approximate this. The solution is of the form of some periodic function multiplied by the exponent of time times some constant matrix. So if this matrix has a positive real parts, real parts of the eigenvalues, then there will be some growing mode. So there will be translating into the fluctuations of the spectator on inflaton, there will be instability. So there will be a production of the fluctuations of the inflaton and of the spectator. So a few years ago, my colleague Michał Wieczorek computed so-called Floquet charts. So how this real parts of the Floquet exponents depends on the amplitude of the inflaton and the wave vector of the produced fluctuation. So he found that for alpha parameter of alpha attractors 10 to minus 2, there is nearly no instability there. So the real parts of the Floquet exponents are quite small. However, if we go to smaller values of alpha parameter to 10 to 9 minus 3, then there is the significant part of this Floquet chart in which the real parts of the Floquet exponents are large. So these bounds in which the Floquet exponents are positive are called instability bands. And during the reheating, the fluctuations goes through along these white lines. Here's the amplitude of the oscillations of the inflaton at the end of the inflation, denoted by this red line. So starting from these lines, the modes will evolve along these white lines and goes through various instability bands. And it turns out that, first of all, the instabilities in the spectators are much larger. It's not surprising because there's this extra geometrical term that drives the effective mass of the spectator toward negative values. And moreover, everything goes to larger Floquet exponents with decreasing parameter alpha. So the smaller alpha, the higher is the instability. And in fact, the smaller is the tensor to scalar ratio predicted by this inflationary model. So this is all about approximating our analysis of this model. To go deeper and have more insight into how this model behaves, you need to go to lattice simulations. And recently, we performed a bunch of lattice simulations for this model to study the reheating in this model. And here we see the part, very small fraction of, in fact, what we calculated, but representative part of our findings. So here is how the different components of the energy density in this model evolve in time. So on horizontal axis, we see the number of the efforts. 0 corresponds to end of the inflation. And as we see, the potential energy density of the inflaton in purple dominates the energy density of the universe during inflation. The kinetic energy density of the inflaton increases during inflation, and finally, it dominates over the potential energy density at the end of the inflation. And more or less at the same time, the fluctuations of the spectator are starts to be produced. So this is indicated by the increase in the energy density of the gradient energy density and kinetic energy density of the spectator that grows through our simulation. And finally, sometime later, there is a rapid increase in the energy density of the fluctuations of the inflaton. So the very important parameter for gluing the inflationary period of evolution of the universe to the radiation domination period is so-called barotropic parameter, which is just the ratio of the average pressure over the energy density. And on these two plots, we see the evolution of this parameter through our simulations for two sets of parameters that we simulated. And as we see, because the energy density of the universe is dominated initially by the kinetic or potential energy density of the inflaton, there is a bunch of oscillations. However, at the same time, the fluctuations of both the spectator and the inflaton is produced. So finally, this barotropic parameter tends to go to the value 1/3, which is typical for the radiation domination era. We can go deeper into the mechanism of production of the fluctuations. So here we see how the various modes of the spectator evolve in time. So the deeper red, the smaller is wave number, the deeper blue, the closer to the blue, the higher is the wave number of the mode of the fluctuations. So as we see, just after the end of the inflation, the most infrared modes are produced mainly. And finally, the high K modes are produced later. And close to the end of our simulation, there is a bunch of the production of all modes. So even the highest K modes are produced. And the same happens for both sets of parameters. So we can take a look on the whole spectra of the fluctuations. So the deeper blue means closer to the end of the simulation. So initially, mainly the fluctuations that belong to the first instability bound are produced. However, through the simulation, the higher and higher K modes are produced. And finally, what is denoted by these gray lines, even the highest K modes that fits into the finite lattice are produced. And this production of the fluctuations produces, so the produced fluctuations produces also the gravitational waves. So before I go to gravitational waves, let me point that the same behavior we see for the fluctuations of the inflaton. So the high K modes of the inflaton are produced from the spectator fields fluctuations due to nonlinear effects. And finally, they tend to dominate the energetically budget of our simulation. So these fluctuations of the fields produces the fluctuations of the metric tensor, so the gravitational waves. And we computed the spectrum of gravitational waves that are produced. And we see that there is a bunch of bunch of the production of the gravitational waves near the end of our simulations. So we had to stop our simulation at some point because we lose the precision of our computations due to high production of the high K modes, which spoils the numerical stability of our simulations. However, it turns out that near the end of the simulation, there is a huge production of gravitational waves, and the further studies need to be performed to understand how large is this production. However, this is quite promising path for the further studies in this field. So at this point, we end the part denoted to the geometrical destabilization during reheating, so after inflation. And now I want to proceed to the studies of the geometrical destabilization during inflation. So let me shortly sum up what we learned about what happens after inflation. So first of all, the geometrical destabilization in fact helps us as theoreticians, because we can immediately reheat the universe. Just this allows us to make quite precise predictions about the spectrum of the fluctuation of CMB. However, in the case of the geometrical destabilization during inflation, there is quite a problematic thing, because the geometrical destabilization was seen as a threat to the inflationary models, because there is a possibility that it can produce the deviation of the inflationary trajectory, or even lead to premature end of the inflation, completely spoiling the inflationary models. However, our results of our numerical simulation shows that this is not the case, and the produced fluctuations back react on the inflationary trajectory and prevent the growth of the fluctuations. So let me go into the details right now. So we studied a very simple model in which the inflation is driven by the so-called Starobinsky potential. And then we couple this, we add to this model a spectator field that gets a potential in very simple form, just a master, and couples these two fields using some higher order operator of this form. So finally, the Lagrangian density takes this form as seen here. So we motivate this choice that there is this is some effective field theory, and this 6-dimensional operator comes from some heavy particles that interact with the inflaton and the spectator, and produces effectively this dimension 6 operator, which is suppressed by the scale of this new physics, which we denote by capital M. So in order to get everything consistent, we need to assure that the scale of the inflation, so the value of the Hubble parameter during inflation, need to be much smaller than the scale of new physics, so the capital M. And we studied this simple model in lattice simulations in order to understand what happens if the geometrical destabilization takes place during the inflation. So if you make the computations, you will find that the Ricci scalar for this model is negative and is given by this expression. And the effective mass for the spectator fluctuations can be represented in this form, in which we introduce the slow parameter epsilon. So slow parameter grows during the inflation, and if it hits this critical point, then the whole effective mass of the spectator fluctuations become negative, which triggers the geometrical destabilization. So here are plotted the results of the numerical simulations. They are given by these solid lines. N equal to 0 correspond to the point in time at which the slow parameter reaches the critical value. And on vertical axis, there is a standard deviation of the spectator field fluctuations. So as we see, sometime after the mass of the spectator fluctuations become negative, there is a bunch of production of the fluctuations, which are, however, stopped at some point. Then there is a decrease, and another bunch of production of the spectator fluctuation. So there are a few oscillations with decreasing amplitude, and in another period during which the spectator field evolves nearly linearly. And this happens, as you see, similarly for two sets of parameters. So it's quite surprising that there happens something that stops the production of the fluctuations. In fact, historically, the mechanism was proposed before we performed these lattice simulations. And the results of the model that was proposed previously it was proposed by Krzysztof Turzyński and his collaborators prior to our simulations. So the results of the model are plotted in dashed lines. As we see, qualitatively, it fits quite well. It reproduces that there is a maximum of the production, then there are oscillations, there is a period of another period of nearly linear evolution of the psi field. However, it misses, obviously, quantitatively because it overestimated the amplitude of the oscillations. So the mechanism that was proposed that stops the production of the fluctuations are called kinematical back reaction. So the idea is such that the produced fluctuations will back react on the inflationary trajectory. So the reasoning goes as follows. So the produced fluctuations will produce some background value for the spectator, and these fluctuations of the spectator should be included in the equation of motion for the inflationary trajectory. And there are two places where this should be included. However, the most important one is here. There is a factor in front of the derivative of the potential. And this factor decreases with growing fluctuations. So effectively, the potential is flattened. So the effective potential that is filled by inflaton is flattened. So this causes the inflaton to slow down. So the slower parameter decreases, and the instability condition, which is proportional to the slower parameter, is no longer satisfied. So the production of the fluctuations are stopped. And then the inflaton accelerates, the value of the slower parameter increases, the instability is turned on once again, it produces the fluctuations. The fluctuations back react through this factor, flattens the potential, the inflaton slows down, and so on. So this is why the production of the fluctuations is stopped, and why there are oscillations. And finally, they relaxate, as we saw, to the period of nearly evolution of the spectator field. So we can check this idea. On the left, I plotted the evolution of the slower parameter. So the kinematic back reaction predicts that the slower parameter should decrease, or at least stop growing, due to production of the fluctuations. So as we see, when the production of the fluctuation takes place, there is a maximum of the slower parameter and the decrease. So because the slower parameter decreases, the production is stopped. But then there is another period of the increase of the slower parameter. The production is turned on once again, but this causes the decrease in the slower parameter, and so on. And finally, we reach the new inflationary period that is not along psi equal to 0 trajectory, but along new trajectory in which the psi field is evolving. So-called psi attractive inflation. This is not the end of the story, because it's quite interesting how this happens in real space. So here I plotted how plotted things that help us understand how this really happens. So in the upper plot row, there are plots that show the slices of the spatial distribution of the spectator field. And in the lower row, there are histograms showing the distribution of the spectator field strengths. So we start with some nearly Gaussian random noise. So this is the start of our simulations. And as we see through the evolution of the system, the spectator field tends to homogenize at the length scales of the order of the Hubble parameter. This is shown on this plot. And as we see, the histogram behaves more or less the same as initial. However, when the geometrical destabilization takes place, something strange happens to the histogram. It goes much wider, loses its nearly bell shape. However, in the distribution, it's not so visible because the same patches fits both pictures. However, if you look closer, the scale of the color bar changes by 2 orders of magnitude. So this means that the patches that are somehow got some positive values of the spectator fields goes into much higher values of the spectator field strength, and with negative values initially goes into much lower values. So the modulus of the field strength grows in both types of places. So finally, the histogram splits in two. So there are 2 peaks that correspond to just separated domains, which correspond to plus and minus more or less the same field strength of the spectator field. So the universe is separated into the patches, and in each patch we have another period of the so-called sidetracked inflation. So the inflation that precedes not along psi equal to 0, but some other trajectory with evolving psi. But there are just patches with positive psi and negative psi, and they are separated. There are domains and domain walls. So to get some general overview how this happens, here I have a plot that shows this. So I just tagged once by another the histograms. The number of the numbers in bins are encoded by the dip of the blue here. And on the vertical axis, we have the number of the equals from the start of ours, from the time at which the effective mass goes to 0. So initially, we see that the distribution of the psi field is quite narrow. It evolves, but at some point, there's a geometrical destabilization that takes place. And the histogram is split into 2 branches. And each branch is like the same as the another, but with the opposite sign. And in each branches, we observe these oscillations. And then another period of the inflation, which goes through sidetracked inflation. So let me sum up. Geometrical destabilization may take place in multi-field inflationary models with negative curvature of the field space. So this is a crucial thing, that this field space is not flat, it's curved and has negative curvature, because then there is a new contribution to the effective mass of the fluctuation that is negative and drives the wall fluctuations, instability of the fluctuations due to driving the effective mass to be tachyonic. So these non-canonical kinetic terms that are responsible for this non-trivial geometry of the field space can come from the UV completion of the model, or can be included from effective field theory approach. So they are quite natural things to be included in inflationary models. So talking about reheating in flat reactors, lattice simulations prove that short wavelength fluctuations of the inflaton are produced, and they are produced by nonlinear integrations of the spectator ones. Moreover, we observe that there is a quite intensive emission of gravitational waves in alpha reactors, which needs further studies. In case of the geometrical destabilization during inflation, the kinematical back reaction is the mechanism that stops the growth of the fluctuations, and it has been recently confirmed in numerical lattice simulations. And the final output of the geometrical destabilization of the during inflation is not its premature end, but another period of the inflation which is sidetracked. Thank you for your attention.